Hello everyone, welcome to the Aperi's Math YouTube channel. Let us start the first chapter, vector space and the subspace. Before starting our main concept of the vector space, we understand about the four concepts: set, binary operation, group and field. What is set? Set is collection of the well-defined distinct objects or the element. Set is nothing but just the collection of the element. But that collection should be well-defined. Well-defined means there should be no confusion whether a particular element is in the set or not. For example, collection of the even natural number. This collection forms the set. As we clearly know that the elements belongs to the set are 2, 4, 6 and so on. Next example is collection of good students in your class. Since the term good is a subjective term and it has the different meaning for the different persons, means this collection is not unique. Therefore, this second collection does not form the set and the first forms the set. Second concept is binary operation. First, we understand about the operation. Operation is nothing but just a rule, which is usually represented by the star. In this process, we are provided with the input, we apply the rule, and we get the output. For example, we are given the three number and the rule is we have to add these numbers. So the resultant is what? 6. Next is binary operation. Binary means 2, means the operation which is applied on the 2 element. That is, let S be any non-empty set. Here we are given the input, means the any two element from the set S. We apply the operation and we get the output. Output is when A and the B are operated. The resultant should also be in the same set S. Then the star operation is called the binary operation. That is, for all elements belong to the set S, when we operate them, the result should belongs to the same set S. Next is group. Group is also a set. Let G be any non-empty set. And star be any binary operation. If this set satisfies 4 property with respect to the operation star, then we called that set to be a group. What are these 4 properties? One is the closure property. Second is associative. Third is identity. And fourth is inverse. First, we understand about all these 4 properties. Closure property. Closure is nothing but the binary operation. That is, let us consider any two element from the set G. If we operate them, A star B must belong to the same set G. Next is associative property. Let us consider any three element from the set G. If we operate B and the C first and then A, or we operate A and the B first and then operate the C, both should be equal. Then we called the set satisfies the associative property. Third is the identity. Identity of the group is a unique element, and we usually give the notation to them E. E is an element of the G. What is the property it satisfies? It satisfies that when we operate any element of the group, it gives the same result, that is A. Then E is called the identity of the group. Fourth is the inverse. If every element of the group has the inverse element, then we called group satisfies the fourth property also. So how we find out the inverse of an element? Let curly A be any element of the set G. If we are able to find out an element in the set G such that if we operate A and the B, the result should be E. E means identity element. Then we called B is the inverse of A. B is inverse of A. So if a set satisfies all these four property, then the set is called the group, and we usually give the notation to the group G star. Let us consider some examples. First is, let the set G is the set of natural number and the operation is the addition. It satisfies the first property. Why? Because the sum of the two natural number is a natural number. Second is the associative property. Since addition satisfies the associativity, this implies the second property is also satisfies. That is, if A plus me, B plus me, C, first we add B or the C and then add A, or if we add A and the B first and then add C, both the result should be equal. Third is the identity. Identity is, what is the identity of the set? Let A be any element of the set. So we have to add such number that their sum is equals to the A. So what is the element? Element is 0, but that element should belongs to the set G. But 0 does not belongs to the natural number, means this does not act as the identity of this set. This set does not satisfy the third property, it does not forms the group. Next example is, let the set is the set of the integer and the operation is addition. First property is satisfied as sum of the two integer is an integer. Second also hold as addition holds the associativity. Third property is the identity. Here 0 act as an identity, but the 0 also belongs to the set of the integer. This implies this set has an identity element and that element is the 0. Fourth is the inverse property. Let A be any element of the set S or the set G, which is the set of the integer. So we have to find out that particular element whose sum is equals to the identity. Identity is the 0. What is that element? Minus A. That is 1 plus minus 1 is what? 0. So minus A is the inverse of the element, any element A. This implies every element has an inverse, and which is minus A. All the four properties are satisfied, therefore it forms the group. And we give the notation by Z. Addition is a group. Next is abelian group. Let G be a group with respect to an operation star. This will be a group. This group G is called to be the abelian if it also satisfies the one more property. What is that property? Commutative property. Commutative property. What is the commutative property? Either we operate A or the B, or we operate B or A. Both should be the same. Then we set that the group is an abelian group. For example, let the set G is the same set we have considered set of the integer and the operation is the addition. We already seen that this set forms the group. Now consider A plus may B or B plus may A. Both are equal. This implies the fourth property is also satisfied by this set G. Therefore, Z plus is an abelian group. Next is filled. Filled is also a set. Let F be any non-empty set. Here we deal with the two binary operation, which are given the notation addition and the multiplication. These are just the notation. It does not mean we have to add the element or multiply the element. These are the two binary operation. If this set F satisfies 11 property, then we called that set is a filled. What are the 11 properties? First is F with respect to addition is an abelian group. What is the meaning? Means it satisfies the 5 property. First is the closure property. Second is associative. Third is identity. Fourth is inverse. And the fifth is commutative. What are these properties? We already studied. Closure means let A, B and the C are any element of the set F. Closure means if we operate A and the B, the result is in the F. For all A and the B belongs to F. Associative means if we add B and the C or then add A, or if we add A and the B and then add C, the result will be same. Third is the identity. Identity is a unique element of the set F and it has a property. If we add that element into the A, it provides the A. Here we give the notation just like in the group. We give the notation by E. Here we give the notation 0 to the identity. So 0 is what? 0 is the, since it is with respect to the addition first operation, so we called it to be the additive identity or the 0 element of the set F. Fourth is the inverse. Let A be any element. We have to find out that particular element of the set F. If we add into it, it provides the 0 or the identity. So we give the notation to that element as the minus A. So minus A is the what? It is the inverse of A. These are just the notation. Fifth is the commutative property. That is, if we add A or the B or A, it provides the same result. So if a set F satisfies with respect to the addition operation all these 5 property, we called it to be a abelian group. So our 5 properties are satisfied. Now we understand the next 6 properties. The next 5 properties are F star with respect to the second operation is an abelian group. What is the F star? F star is all the element of the set F excluding one element, and that element is the 0 element or the additive identity of the set F. So what are the 5 property? Same. First is the closure. Second is the associative. Third is the identity. Fourth is the inverse. And then commutative. So the first is the closure property. Closure means we multiply any 2 element of the F star, the result is in the F star. Second is the associative. That is, if we multiply B or the C first and then A, or we multiply A and the B first and then C, the result will be the same. Third is the identity. Here the notation which is provided to the identity is the 1. That is, 1 is called to be the multiplicative identity. What is the 1? 1 is multiplicative identity. If we operate any element with the 1, the result is the same element. Fourth is the inverse. That is, we have to find out that particular element from the set F star, that if we operate with the A, the result is to be the identity, which is given the notation 1. Another is the commutative. Either we operate A or the B or the B or A, the result is same. Now the last property is distributive property. Left distributive and also right distributive. If we operate B plus C with the A, we get the result AB plus AC. Similarly, and if a set satisfy all the 11 property, we called that set to be the filled, and we give the notation F addition and the multiplication is filled. Let us consider some of the example of the field. First is, let the set f is the set of the natural number and the binary operation is addition and the multiplication, ordinary addition and the multiplication. So in order to check whether this set forms a field or not, first we check set of the natural number with respect to addition is abelian group or not. As we already seen that this set does not has the identity, this implies this is not an abelian group. This implies this set does not form the field. Second example is, let field is the set of the integer and the binary operations are the addition and the multiplication. Now you have to check and write in the comment section whether this set forms the field or not. This is a homework question. Now the next example is, let the set is the real number and the operation are addition and the multiplication. First we check whether R with respect to addition is abelian group or not. First is the closure property. Since sum of the two real number is a real number, means it satisfies the first property. Second is the associativity. Since addition holds the associativity, therefore it also satisfies the associative property. Third is the identity. 0 here acts as the identity and 0 also belongs to the real number. Therefore the third property is also satisfies. Fourth is inverse property. So every element has an inverse which is minus a. Let a be any element, and if we add minus a into a, we get the 0 which is the identity element. Therefore every element has the inverse also, and the addition operation is a commutative. Therefore it satisfies all the 5 property. Next is R star. What is the R star? R set of the real number minus me additive identity. What is the additive identity? 0. That is R minus me 0 is abelian group or not. First is the closure property. Since multiplication of the two real number is a real number, so it holds the first property. Since multiplication holds the associative property as a into b into c or a into b into c, both are equal, therefore it holds the associative property also. Third is the identity. Identity is if we multiply any number with the 1, we get the same number, therefore 1 here acts as an identity element. Fourth is the inverse. So we have to find out that particular element B whose multiplication with the A give us the 1. That element is what? 1 by A. And A is non-zero. Why? Because the element belong to the R star, and in R star we have exclude the element 0. This implies every element has the multiplicative inverse also, and that is 1 by A. Fifth is the commutative property. As multiplication satisfies the commutativity, therefore it holds all the 5 property also. Next is the distributive property. Since multiplication is distributive over the addition, therefore it also holds the distributive property. Therefore, set of the real number with respect to binary operation, addition and the multiplication form the field. Now you have to check yourself whether set of the complex number with respect to the addition, ordinary addition and the multiplication forms the field or not. Now we start our main concept, vector space. Till now we learned about the algebraic structure such as group, field, in case of the group we deal with the one set G and the one binary operation star. In case of the field we deal with the one set and the two binary operation which are called addition and the multiplication. In case of the vector space, here we deal with the two sets. One is called the V and the another is called the F. Since we are dealing with the two different sets, so in order to not to be the confused whether an element belongs to the set V or F, we called the elements of the V as the vectors and the elements of the F as the scalars. These terms, vectors and the scalar, does not has anything to do with the magnitude and the direction, the concept which we studied in the physics. This set F is nothing but the field. This set V also work on the two binary operation. But what makes it different from the other algebraic structure is that here we are dealing with the two different types of the binary operation. One is the internal binary operation and another is external binary operation. The binary operation which we studied till now consider the internal binary operation. That is, if I take u and the v, any element of the set V, and if we operate u and the v, the resultant is also in the set V. However, in case of the external binary operation, we have the two sets let V and F are two non-empty set. Since it is a binary operation, so it is applied on the two element, but the one element is in the set V and the another element is from the set F. So let U is an element of the V and A is an element of the F. Are given the input A and the U, and if we apply an operation on them, A is operated with the U, the resultant is in the one of the set and that set is the V. Then we called this operation is an internal binary operation on the set V. We can say the internal binary operation is a function from V cross V to the V. We are taking the two elements from the set V, operating them, the resultant is in the V. And the external binary operation is a function from F cross V to the V. We are taking an element of the F, operating it with the element of the V, and the resultant is in the V. Let me summarize what we have studied till now. That is, in case of a vector space, we deal with the two set V and F. This F is nothing but a field, that is, F with respect to addition and the multiplication is a field. And the elements of the F are called scalars. The elements of the V are called the vectors. Just like in case of a field, we give the name to the binary operation as addition and the multiplication. In the similar way, we give the name to the binary operation as vector addition, which is denoted by the addition, and the second is the scalar multiplication. So how we define the vector addition? Let U and the V be any two elements from the set V. Then if we operate them, their resultant should be in the V. How the scalar multiplication is defined? Let A be any element from the field F and U be element from the vector V. If we operate A and the U, the result is in the V. Now a question arises, why the elements are only given the name as the vector and the elements of the set F as the scalars? So I don't know whether it is correct or not. But as per my thinking, as the sum of the two vector is a vector and the product of a vector with a scalar is a vector. This is the vector v1 and the another vector is I plus me j cap. So what is the sum of these two vectors? It is 3i plus me 4j cap. So the sum of the two vectors is a vector. Therefore, vector addition is a what? If we take the two vectors, their sum is also a vector. Next is let 2 is any scalar and this is a scalar and we are given the vector v1. If we multiply 2 with the vector v1, we get 4i plus me 6j cap, which is a vector. That is, if we multiply a scalar with the vector, the resultant is vector. And usually we do not give any notation to the multiplication of the scalar with the vector, as it is obvious that we have to multiply both of them. In the similar way, we do not give any notation to scalar multiplication binary operation. And if this set V satisfy 10 property, then we called this set V as a vector space over the field F. What are these 10 properties? First 5 are V with respect to the first operation, which is vector addition, is an abelian group. Means it has to satisfy the closure property. Second is the associative. Third is the identity. And the fourth is the inverse. And the fifth is commutative. The another 5 properties are, first is the external binary operation. It is like the closure property. Closure means internal binary operation. But here we are dealing with the, in case of the scalar multiplication, we are dealing with the external binary operation. That is, let A be any element of the set F and U be any element of the set V. If we operate A and the U, the resultant is in the V. Just like the associative property, here is Let us consider A and the B be any element of the set F and U is any element of the set V. Either we operate A and the B first and then operate U, or we operate B and the U first and then operate V. Both should be equal. Here, identity is like let 1 belong to the field F. 1 is the what? It is the multiplicative identity of the field. And if we operate 1 with any element of the vector V, the resultant is equal to the V for all V belong to the set V. Fourth is not like the inverse property. Fourth is the distributive property. Fourth is like the distributive property. Here we have the from the left hand side and the from the right hand side distributive. That is, if A plus may B of the U is equals to AU plus may BU, and A of U plus may B is equals to AU plus may AV. So, if a set satisfies all these 5 properties, we called that set is a vector space over the field F, and we give it the notation V over F is a vector space. With respect to the two binary operation, one is the vector addition and another is the scalar multiplication. Question number 1. Prove that the set of all the vector in a plane over the field of the real number is a vector space with respect to vector addition and the scalar multiplication. Let V be the set of all vectors in the plane. And the field F is the field and which is the set of the real number. We are not provided any operation of the field, and we know what is the usual field with respect to the set of the real number. It is R with respect to the addition and the multiplication. So this is the field. What are the elements in this set? For example, let this is xy plane. Here is any point x comma may y. So we can represent the V as the tuples x and the y such that x and the y belong to set of the real number. And the operation with respect to the vector V are the vector addition and the scalar multiplication. How the vector addition is defined? The symbol is the addition and here is the scalar multiplication. Or we can say this is an internal binary operation and this is external binary operation. It is defined as let U and the V are any element of the set V. Therefore, U is equals to U1, U2 and V is equal to V1, V2. How the vector addition is defined? When we add U plus V, they are added component wise. That is U1, U2 plus V1, V2 is equal to the u1 plus me v1, comma u2 plus me v2. How the external binary operation is defined? Let E be any element from the field. Field is the set of the and U, which is equal to the u1 comma me u2, where u1 and the u2 are the element of the set of the real number. This is the element belong to the vector V. Belong to the set V. So external binary operation is defined as when we multiply A with the u1 and the u2, A is multiplied component wise. That is, it is equal to AU1, comma AU2. Since product of the two real number is a real number, therefore this set must belongs to the set V. Now we check whether this set V with respect to the operation addition and the scalar multiplication satisfies all the 10 property or not. So the first property here is the what? That is V with what are the first 5 property with respect to the addition is V with first property is closure property. Let U and the V are the two element from the vector V. So U plus may V, we already seen it is in the set V. Closure is nothing but the internal binary operation. Second is the associative property. Let U, V and the W are the three elements of the set V. This implies U is equal to U1, U2, V is equal to V1, V2 and W is equal to W1, W2, where this UI, Vi and the Wi belong to the set of the real number. So first we add U and the V and then we add W. What is the result? Result is if we add both of them, we will get as they are added component wise. So we get U1 plus me V1, U2 plus me V2. Then we have to add W1, W2. It provides us U1 plus me V1 plus me W1, U2 plus me V2 plus me W2. This is also equal to the U1, U2 plus me V1 plus W1, V2 plus me W2, as their sum is nothing but equal to U1 plus me V1 plus me W1 and U2 plus me V2 plus me W2. And this is equal to the U plus me V plus me W. Therefore, associative property is also satisfied. Third property is identity. Let U be any element from the set V. Since if we add U1 and the U2 with the 0, 0 element, we get the same element U1 and the U2. Therefore, 0, 0 act as the 0 element or the additive identity of the set V. Fourth is the inverse property. let U be any element from the set V. So we have to find out that particular element. If we add that element into the set U, we get the identity, that is 0, 0. So that element is minus U1 comma minus U2. As what is the sum of this? U1 minus U1 minus U1 comma U2 minus me U2, which is equal to 0 comma me 0. Therefore, minus U1 comma me minus U2 is the inverse of any element U belong to the V. Therefore, every element has an inverse. Therefore, it satisfies the fourth property also. Fifth property is commutative property. Either we add U or the V, or we add V or the U. The result is the same for every element U and the V belong to the vector space V, because addition holds the commutativity. Therefore, the first 5 properties are satisfied. Now we check the next 5 property. First property is external binary operation. It satisfies it. As we already seen, if we multiply set of the real number with the element of the V, we get the element of the set V. Second is the let E and the B are the two elements of the field. Field is the set of the real number. And V is the vector. We have to check. If we multiply A and the B and then with the vector V, we get the same result if we multiply B and the V first and then A. So what is the vector V? Vector V is V1 comma V2, where V1 and the V2 belong to the set of the real number B of V1 comma V2. How we define the scalar multiplication? The scalar, this is a scalar, that is the set of the real number, as the product of the two real number is a real number. So how it multiplied? A B V1 comma A B V2. This is equal to A. The first B is operated inside B V1 comma B V2, and then we have A B V1 comma में A B V2. As left hand side and the right hand side is same, therefore the second property is also satisfied. Third property is like identity. Since the field is the set of the real number with respect to addition and the multiplication, we already seen 1 here act as an multiplicative identity. And if we multiply 1 with any vector V, means we have to multiply it component wise. We get the same result. As this implies third property is also satisfied. Next is the distributive property. So let A, B and the C be any element of the field, and U and the V are the element of the vector space V. So we have to check whether A plus me B of U is equal to AU plus me BV, and we have to check also A of U plus me V is equal to AU plus me EV. So you have to check by yourself that both these property also satisfied. This implies that this vector space V has satisfies all the 10 property. Therefore, V is a vector space over the field F and we represent it as V over me. F is a vector space. In the next lecture, we solve some more questions of the vector space and also the property of the vector space. Thank you for watching the lecture. If you find it beneficial, please like, share and subscribe.